Okay, hello everyone, Mr. Heisinger here. I'm going to talk you through section 5.2. Very long section. I'm going to try to break this up into probably at least 3 different lessons. We're going to concentrate mostly on energy today, and then we'll look at kinetic energy. Now, your book does not spend a whole lot of time talking about energy in general, but energy is such an important topic in physics overall. I don't want to get into kinetic energy until we talk a little bit about what energy is just in general. So 8th grade textbook pictures, you may have seen something like this before. Thermal energy, chemical energy, electrical, light, pressure, nuclear energy, all different forms of energy that we could talk about. Energy of vibration, food energy, energy that we get from electrical supplies and so forth. These are just pictures of nuclear energy sources. So fusion and fission are two of the two nuclear processes. A lot of nuclear energy, nuclear power plants in the U.S., much more in the other parts of the world. Here we have chemical energy. When we burn fossil fuels, we break some chemical bonds, form other bonds. We get heat generated from that energy transformation, and we can use that heat to maybe generate some heating in our home, or we could use that to generate thrust and so forth. Here we have renewable resources, gravitational potential energy. Waterfalls allow us to convert gravitational potential energy into other forms of energy down here so that we can do work on various things. You're familiar with solar energy and then wind energy. You're starting to see a lot more wind farms popping up. Let's talk about how we define energy in general. Energy is roughly defined as the ability to create change, closely related to the concept of work. You can think of energy as the ability to do work, and work is really just a transfer of energy. And again, this is the idea of work being force times distance. FD cosine of theta, like we talked about in the last section. So when we do work on something, we actually transfer energy. A lot of that energy starts as probably chemical energy, energy within our body from the food that we've eaten. And then we do work on various things, apply a force through distance to be able to transfer the energy that we have in our body to the energy in that object. Now, how do we measure an amount of energy? By looking simply at how much change it can create. So we want to quantify energy here. There's 5 different objects that I want to look at here, and you're probably more familiar with the energy of a Snicker bar than you are with the energy that we might talk about in science. So let's start with the definition or the units for energy in science. The SI unit for energy is the joule, just like it is for work. And that should make sense, since work is the transfer of energy, energy is the ability to do work, they should have the same units. 1 joule, energy expended when 1 newton of force acts over 1 meter of distance. When you do 1 joule of work, you transfer 1 joule of energy from you to something else. And so it's the SI unit for both energy and work. Now you're more familiar probably with the energy, food energy, and the unit for food energy is the calorie. So a Snicker bar, lots of food calories. Let's take a look at some numbers here. First, the definition of the calorie. It's the amount of energy needed to raise 1 gram of water 1 degree Celsius. Now, in reality, that's just a single calorie. When I say that a Snicker bar is 270 calories, that's actually 270 food calories. Well, that's 270,000 of these calories. So, food calories are actually kilocalories. Now, we don't call this here, we don't say 270,000 calories. No one would ever eat a Snicker bar again. That's a lot of, that would be way too much energy, they'd say. But in reality, it's just the calorie itself is too small of a unit for us to use to talk about food. 1 food calorie is about 1,000 of these calories. Let's take a look at this now. The energy that we might, or the unit that we might talk about for fuel coming out of our burner on our stove is actually probably BTUs. You may have heard of those before. That's the British thermal unit. It's really just the amount of energy needed to heat 1 pound of water by 1 degree Fahrenheit. Same idea as over here, how we define the BTU, except we're dealing with a different amount of mass of water and a different temperature scale, but similar concept. Now, fuel that we put into our car. The fuel that we put into the car gives the car ability to do work. We can drive that car all around. Let's take a look at 1 gallon of gasoline. 1 gallon of gas is equivalent to 114,000 BTUs, if you want to think of it like this. If I have 114,000 pounds of water, maybe a swimming pool in my backyard, If I were to burn a gallon of gas, I could, and heat that water up, I might be able to change 114,000 pounds of water by 1 degree Fahrenheit. Now there's other ways that we could equate or compare that gallon of gas in different forms of energy, different units of energy. 33.41 kilowatt hours. Hard unit to understand. We'll study that more in section 5.4. Food calories is probably, now we can do a comparison between this, the candy bar, and a gallon of gas. Maybe $1 for a candy bar, 270 calories there. Over here, 1 gallon of gas is equivalent to 31,500 food calories, a tremendous amount of energy contained in that gasoline. Pound for pound, $1 for 270 calories versus maybe $3 or $4 for quite a bit more energy. Now we can talk briefly, I don't want to spend too much time on this here, but energy density. Gasoline is a very energy dense substance, which means it contains a lot of energy per unit volume, as opposed to mass density where you say so much mass per unit volume. This is more about how much energy we pack per amount of substance, and so energy, or gasoline rather, is a very energy dense substance. Let's take a look at food energy. This is not food energy, this is don't eat this. This is electrical, these are batteries just to illustrate electrical energy. We might use electrical energy to drive our substances, or our appliances rather, as opposed to food energy driving our body. So just another form of energy. Now the kilowatt hour is the unit that we use to describe electrical energy. The kilowatt hour, again, sort of hard to understand. If I have a 1,000 watt device, could be my toaster, could be my microwave oven, maybe it's a really bright light bulb. A lot of light bulbs you see are like a 100-watt light bulb. Well, this is 1 kilowatt. So if I have a 1 kilowatt toaster and I run it for 1 hour, I would use 1 kilowatt hour of electrical energy. And finally, let's just take a look at wind energy. Wind energy in the United States only accounted for about 3.46% of all of our generated electrical energy. We really do need to use wind energy quite a bit more. We have a lot of resource out there, and you're seeing wind farms popping up all over the place. Let's take a look at doing a quick energy conversion calculation. Let's say I eat a candy bar, 270 food calories. That's 270,000 of those other simple calories that we talked about. That's chemical potential energy. I'm going to use that food to do physical work. So I'm going to climb some stairs. Let's say that my body can convert about 20% of the food energy into physical work. I can actually convert about 20% of it. I'm not completely efficient. If you're really interested in reading about how the body converts that, you can take a look at this, pause it, read through that, and it gives you some information. Otherwise, let's jump right into this. So how many times can a 75 kilogram student climb the stairs from the first floor to the second floor? Now the stairs are 5 meters up. We have four different scenarios we can go through. This one here is just going up a really steep set of stairs. This is a little bit shallower stairs. This is shallower yet. Maybe it's a ramp of some sort going up to the top of those stairs. And here's a situation where you could just climb a ladder. Now, this might surprise you, but the amount of work he does against gravity in every one of these situations is exactly the same. And I want to try to explain how that works. Let's consider him being on a ramp or an inclined plane. As we talked about before, the weight force acts always downward. Well, we would typically resolve that into two components, a weight force into the plane and a weight force down the plane. Well, the shallower that angle, the less the weight force acting down the plane. So what he's going to end up having to do is just exert a force up the plane that's equal to this component. So what he ends up doing is he's exerting a fairly small force, but over a pretty big distance. So what he's doing is he's using an inclined plane to exert less force over a greater distance. He still does work equivalent to small f times big D. Now if we put him over here on this ramp, it's a much steeper incline, which means he has a much greater weight force acting down the plane because of the steeper incline. He has a smaller weight force acting into the plane. Well, for him now, he's going to have to exert a greater force up the incline. So now what he has is a much larger F that he has to exert, but he has to do that over a smaller distance. He still ends up doing the exact same amount of work. The product of force times displacement, which is work, is the same in any of these cases. And this is just an intermediate example between those two. if we were to look at this one. So let's do the simple one. Let's have him just climb this ladder. In this case, the amount of force he has to exert is just simply equal to his weight. And the distance he has to travel is not along this incline, it's really just the height that he goes through. So in order for us to calculate the work, it's a little bit simpler. Work is just force times distance cosine of theta. In this case, the force is his weight. D is the height of the stairs. And the cosine of theta is just 1 because theta is 0 degrees. The force that he exerts is in the direction of his motion. The force that he exerts is equal to his weight, and the direction is straight up, so he does positive work. Now we can plug in some numbers here. M times G times H cosine of theta. This is just a way to calculate the work that he does, and hopefully you can follow through with that math. That's how much work he does in climbing the stairs. Whether or not he climbs them like this, or he climbs them on any of these paths, he does the same amount of work in all those cases. Now if he has to burn off 20% of this amount of energy, let's first determine how much 20% is. 20% of this much energy is 226,000 joules. Well, if he has to burn off that much energy and he burns off this much energy per climb, then the number of times he could climb those steps is about 60 times. So 1 candy bar, you're going to have to climb those steps about 60 times to burn off that energy. Now we have different forms of energy that we're going to quantify here. We want to look at kinetic energy, and then later on we'll talk about potential energy. Let's talk about each of these briefly. Winds do work on the blades as they slow down. So as the winds come in and hit these blades, they can do work on those blades and cause them to spin. Those blades would be connected to a generator of some sort, generating electrical energy. So what is kinetic energy? Kinetic energy is simply the energy of motion. The ability to do work because something is moving. Now there's an equation, it's 1/2 mv squared. This is by definition, it's not derived from anything else. This is simply what we call in optics KE. Depends on mass and velocity squared, and then we have that half in there. The SI unit is the joule, just like it is for energy, for work, you name it. It's a scalar quantity, it has no direction. So even though the wind is blowing maybe with quite a bit of a velocity this way, maybe blowing towards the east, kinetic energy has no direction. Now we also have potential energy. Potential energy is simply energy of position. Now this is a more complicated topic. We'll study this in another day. But energy of position is really just stored energy, whereas this is energy actually in motion. This has the potential to do work as it changes from one position to another. So we can talk about high energy and low energy positions. If I think of this as being a high energy state, as that wrecking ball moves to a lower energy state and swings through here, as it does that, we see that it has the capacity to do work, and maybe it's going to hit some building over here and it can do work on that building and knock it over. Here's another form of potential energy. It's called elastic potential energy. As he pulls that string back, he ends up curving that bow and causing it to change its shape. There's actually energy stored in that shape of that bow. As that bow goes back to its normal relaxed position, if you will, it's going to end up doing work on that arrow. And when it does work on that arrow, it increases its kinetic energy, and so it comes off at a pretty high rate. Again, we'll study this kind of stuff later. Now, we want to explore kinetic energy in a little bit more detail. Wind speed increases with elevation, but density of air decreases. So are we better off placing turbines really high up into the air in order to take advantage of the high wind speed? Or are we better at placing them lower on the ground and taking advantage of more mass? So which of these things contributes to the kinetic energy more? You probably know the answer if you've seen the wind farms out there. They usually have the turbines up way in the air, and that's because we want to take advantage of that really high velocity. Makes sense if you look at that equation. The speed is squared in that equation, which means that it has the bigger effect. Since speed is squared, doubling your speed quadruples your kinetic energy. Tripling your speed, if I go from like 20 to 60 miles per hour, that's going to actually increase the kinetic energy by 9-fold. Again, it's because of that square in there. 2 squared is 4, 3 squared is 9. So we have a great dependence on speed. Now I want you to be able to do some calculations here. And again, these are straightforward calculations just using the equation KE is 1/2 mv squared. So this is the main equation that you would use for this. And to be honest, it's really straightforward to calculate these things. I want you to do those. You're going to stop the video, try those problems, and then we'll see whether or not you get them right. The only thing I do want to share with you is how to convert 12 miles per hour into the SI unit for speed. Just simply multiply that by 0.447. We spent a lot of time in the first trimester dealing with conversions. Now I want you to just be able to use this to get to energy ideas. So go ahead and give that a shot, see how you do, and then come back and check and see how you did with those answers. So hopefully now you've had a chance to be able to do that. And here are your answers for these calculations. The kinetic energy of the car, just 1/2 mv squared, is about 560,000 joules. Kinetic energy of the baseball, you did have to convert that grams into kilograms, SI unit idea. 165 joules. The bowling ball is about 73 joules. And the bullet, very striking I think to me, was that the bullet actually has a tremendous amount of KE, largely because of its speed. 391 meters per second is greater than the speed of sound actually. These are actually shock waves that you're seeing up here. So a tremendous amount of energy. Again, based on that speed being squared. Now, down here, how fast would the baseball need to be thrown in order for it to have the same KE as the bullet? I want to tell you this 46 meters per second is about 100 miles per hour, so that's a major league pitch. Could he possibly throw it fast enough so that the ball had the same capacity to do work as the bullet? That would be equivalent to its kinetic energy. And to do that calculation, what I'm going to end up doing is I'm going to set the kinetic energy of the baseball equal to the kinetic energy of the bullet, and then solve that for V. And if you go through and follow along with that mathematics, you'll see that V is just plus or minus the square root of this value up here. That'd be plus or minus 113 meters per second. That's about 250 miles per hour. That's a major league throw. More than likely not going to be able to do that ever. So 113 meters per second, very high speed. Should be able to do this kind of calculation. Guys, in a nutshell, that was section 5.2, the very first stages on energy in general, which again your book does not describe very much. I wanted you to have a basis understanding of what that is before we get into different forms of energy. And then this is on kinetic energy. Now it's a very short lesson. Honestly, there's not a lot of stuff there for you to practice on. So I'm going to go back to your learning targets. This is what I want you to be able to do, and you should be able to do these actually without much difficulty using that equation. So practice B125. I'm going to ask that you read through and do these couple of problems. These are actually on the work kinetic energy theorem, but you know what? I think you can get that from reading, looking at the practice problem right before they give you the practice C things. The work kinetic energy theorem is difficult when we look at applications of it, but these things here I think you can get just from the reading. We'll talk about this more tomorrow. Okay guys, that's it. Good luck, and we'll see you tomorrow. Go Bucks.